All right, welcome to The Explainer. Today we are jumping into a really powerful calculus technique. It's called integration by parts. And let me tell you, this is the tool you pull out when all the other simpler methods just don't stand a chance.
So let's kick things off with a classic calculus puzzle. You've probably seen this before. How in the world do you integrate a product of two totally different kinds of functions? Like an algebraic function like x getting multiplied by a trig function like sine of x. Your usual go-tos like u substitution, yeah, they're not going to work here. And that right there is exactly where integration by parts saves the day.
Okay, so here's our game plan for today. First, we're going to break down the master formula itself. Then I'll let you in on the secret weapon for using it, this thing called the Lie strategy. After that, we'll walk through some guided examples, try a few practice problems for ourselves, and even see how this stuff pops up on exams. And of course, we'll wrap it all up with the key takeaways you've got to know. All right, let's get right into it. We're about to add two absolutely essential tools to your integration toolkit. We've got the master formula, that's the engine behind all of this, and then this just brilliant little strategy that helps you apply it perfectly, every single time. Okay, so here's the big idea. You remember the product rule for derivatives, right? Well, if you do, you're already halfway there, because integration by parts is basically just that rule, but backwards. What it lets us do is pretty clever. We get to trade a difficult integral for, hopefully, a much easier one. The whole game, the entire strategy, is to pick our pieces so that the new integral we get is something we can actually solve. But that begs the question, right? How do you actually choose which part is u and which is dv? Well, this is where the real magic comes in. It's a simple, super handy acronym, LIAT. Seriously, this thing is your key to success. Think of it like a priority list. When you're picking your u, you start at the top. Do you see a logarithmic function? Bam, that's your u. No log? Okay, how about an inverse trig function? You just go down the list, and whatever you pick for u, the rest of the stuff in the integral, that's automatically your dv. All right, theory is great and all, but let's be real. Seeing this thing in action is where it's all gonna click. So let's jump into some guided examples and watch how this formula works step by step. So for our first example, we've got the integral of x times e to the 2x. Okay, let's think about our LIAT rule. We've got x, that's an algebraic function, and we've got e to the 2x, that's exponential. In LIAT, a comes way before e. So this is a no-brainer. Our u is going to be x. Now, trust me on this. Setting up a little table like this is the absolute best way to keep everything straight. We've already got our u and our dv, so now we just need the other two parts. First, we differentiate u to get du. Well, the derivative of x is just 1, so du is simply dx. Easy enough. Next, we integrate dv to find v. The integral of e to the 2x is 1/2 e to the 2x. And just like that, perfect. We have all four pieces of the puzzle ready to plug into our formula. And these next examples, the ones with the natural log function, really show you just how powerful that LIAT rule is. Remember how L is right at the top of the list? That means if you ever see a logarithm in your integral, it is almost always going to be your u. It's such a great shortcut. Takes all the guesswork right out of it. Okay, now, things are about to get a little more interesting. See, some problems are just, well, they're a bit more stubborn. Take this one here, the integral of x squared times sine of x. For this bad boy, you actually have to use the formula not just once, but twice to crack it. So the strategy is a two-pass approach. On our first go-around, we pick u equals x squared. Now that's not going to solve the whole thing, but watch what it does. It knocks the power of x down from a 2 to a 1. So now we're left with a simpler integral. And from there, we just do it again. That second pass gets rid of the x completely, and suddenly we're left with a really simple integral that we can finally solve. Okay, last but not least in this section, let's see how this all applies to definite integrals. You know, the ones with limits of integration. The process is pretty much the same. First, you use integration by parts to find the antiderivative, just like we've been doing. But then you've got that extra final step. You evaluate your answer at the upper and lower limits and find the difference. All right, we've seen the examples. Now it's our turn to get our hands dirty. It's time to put these new skills to the test and work through a couple of practice problems. This is where we're going to make sure this technique really sticks. Let's start with an absolute classic indefinite integral, x times the cosine of x. This is a perfect, straightforward problem to try out our new method on. Okay, let's break this down together. First up, LIAT. We've got x, that's algebraic. We've got cosine of x, that's trigonometric. A comes before t, so our u is x. That makes du just dx. The rest, cosine of x dx, is our dv. We integrate that, and we get v equals sine of x. Awesome. Now we plug everything into our formula. uv minus the integral of v du. That gives us x times sine of x minus the integral of sine of x dx. And what's the integral of sine? It's negative cosine. So that double negative flips to a plus. And what's the one thing we can never, ever forget with indefinite integrals? You got it. Slap a plus c on the end.
Okay, next up, a definite integral. The beginning of this problem is going to feel exactly the same. We just have to remember that crucial final step at the end, where we plug in those limits.
So we set up our table, same as always. U is x, dv is cosine of 3x dx. We do our thing, we differentiate and integrate to find du and v. Then we plug it all into the formula, do a little bit of simplifying, and boom, we have our antiderivative. Now we're ready for the big finale. And here it is, that final, crucial step. We take our upper limit, pi over 6, and we plug it into the entire antiderivative. Then we do the same with our lower limit, 0, and we subtract the second result from the first. Now, be careful. A super common mistake is to forget to apply the limits to the whole expression. You've got to be really meticulous here. Once we crunch all the numbers, we land on our final answer, pi over 18 minus 1 over 9.
Okay, let's switch gears and talk about how this stuff actually shows up on exams. Because let me tell you, examiners love this topic, and they tend to have a few favorite ways to test if you really know your stuff. Here's a classic exam question setup. You get two problems that look almost exactly the same, but that first move you make, it's everything. For the integral on the left, you've got algebraic versus exponential. Lyautey says a before e, so u is x. But for the one on the right, you've got that logarithmic function. L is at the top of the food chain, so u has to be ln of x. This is just a perfect example of why you absolutely have to have that Lyautey rule down cold. And would you look at that, our old friend, the two-step problem. If you see something like this on an exam, it's basically a big flashing sign. It's testing not just that you know the formula, but that you can follow a multi-step process without getting lost. It's a huge clue that you're going to have to apply integration by parts twice. Okay, so let's wrap this all up. We've covered a lot of ground, so let's boil it all down to the absolute key takeaways. These are the things you really need to have locked in your brain. First, you've got to know that formula by heart. Second, your strategy is always Li8 for picking u. Third, stick to the process. Set up that table, find your 4 pieces, and plug them in. And finally, the big warnings. If it's an indefinite integral, do not forget your plus c. And if it's a definite integral, you have to evaluate from b to a. Simple as that. And there you have it. This is a seriously powerful tool that unlocks a whole new class of problems that used to be impossible. So now that you've mastered this technique, the real question is, what's the most complex integral you think you can solve? This really opens up a lot of doors. Thanks for hanging out with me for this explainer.